Okay, let's start. So this is continue of our week 1 material. So we ended at explaining the meaning of matrix and matrix multiplication. So let's start from some properties of matrix operations. So whenever you multiply two matrices, you need the size of matrices that can be multiplied together. So if you want to get a matrix multiplication A times B, the number of column of A must be equals to number of row of B. Okay, so that's that's only when you can get the matrix multiplication. So whenever you have a suitable size of matrices that can be applied your matrix multiplication in these four equations, this equality holds. So matrix multiplication has associativity rule. So it doesn't matter which operation comes first when you have multiple of multiplications, and you have a distribution rule for the matrix multiplication. Distribution rule. And you can also distribute your multiplication on the right hand side also. So these are distribution rule. And whenever you have a scalar k here, then you can move around your scalar k in between two matrices in multiplication. So that's kind of obvious equation, but you can also prove this equality using the formal definition of matrix multiplication that we discussed earlier, that we have here. So this is our definition of matrix multiplication, but it's a tedious works, and you probably will do this on the linear algebra course, maybe not, but it's not that important. So let's talk about the transpose. At the end of the class yesterday, 2 days before, we talked about how to take the transpose of a matrix in the MATLAB. So let me formally define the transpose here. So whenever you have a matrix A, the transpose is the new matrix where you get the j's row and i's column entry from i's column and i's row j's column entry of the original matrix. So simply you switch row and column to get the transpose of a matrix. So, and then there are other equalities on transpose operations. First one is that if you take the transpose twice, you switch a row and column twice, then you get the original matrix. That's obvious. And also you can move around your scalar multiplication inside or outside of transpose, because if you take the transpose of one real number, it's just the same if you consider a real number as 1 by 1 matrix. And you can also distribute your transpose operation, distribution rule. And this is the most important one. So if you have a matrix multiplication of two matrices A and B, and you want to take the transpose of that matrix multiplication, then you can separate out your transpose, but the order of multiplication changes. So this is important because in matrix multiplication you cannot switch the order of multiplication. This is important because in general AB is not equals to BA if AB and BA are, even if these matrix multiplication are well defined. So you cannot switch the order of multiplication. So usually, in general, this is not equals to A transpose times B transpose, and this may not be well defined. Because whenever you multiply two matrices, like in the left hand side here, let's say A is size of n times m and B is size of m times l. That's only when you can multiply two matrices. This m must be the same. But let's take a transpose of A. Then the size is m times n, and the transpose of B is size of L times M. So you cannot in general multiply AT and BT in this order, because N and L are in general can be different. However, if you take the B transpose with A transpose, then you have the same M right here. So you can multiply B transpose with A transpose. Okay, so that's one thing that you must memorize. However, if N and L are all equal, you may not get the same matrix by taking A transpose times B transpose with the AB transpose. So you always have to memorize this transpose rule. So let's this is probably the almost last property or definitions of matrix, the determinant. Probably you might remember from the differential equation course, that last semester, that you need that determinant to compute the what was the name? When you have a two fundamental solution, you want to check whether these are the fundamental sets of solution or not. You need to compute the determinant of 2x2 matrices or 3x3 matrices. And you probably memorize this, but let me restate that again. If you have a 2x2 matrices, then the determinant is given by multiplying the diagonal entries and then give a plus sign and multiply the off diagonal entries and put the negative sign here. Okay, so that's how you get the determinant. In here, in our multivariable calculus, we will use the determinant of 3x3 matrix often. So here's how you can memorize the 3x3 determinant matrix and determinant of 3x3 matrices. So first, you take all the diagonal entries consecutively, 3 entries. So the way you can get the consecutive 3 diagonal entries are these method. So first you take the diagonal b1, b2, b3, and then you take a diagonal, but you get a different so you take b12 here, b12, and then b23, and then you go back to b31. The reason why we do this instead of taking b13 is that I want to pick an entry of my matrix B in different row and different column. So I don't want any of these 3 entries of B have the same column or same row. So that's how I get these 3 types of triple of entries of matrix B, and then give a plus sign here. Okay. And then you get the off diagonal. Do the same thing for off diagonal. So first you take this one, and then this one, and this one. So you get the negative, give a negative sign for here. So that's the determinant of 3x3 matrix. So this kind of rule to memorize determinant of 2x2 or 3x3 matrix only applies up to the size of 3. When you get a 4x4 matrix or 5x5 matrix, there are other rules, but not like this. But if you know how to get the 2 by 2 or 3 by 3 matrix, like determinant of those matrices, then you can inductively define the determinant of general matrix. And that will be also covered in the linear algebra. We're not going to go deeper into that. Okay, so while we are talking about the determinant, I want to define a cross product. So what is a cross product? So let's say we have two vectors A and B, and I want to find out a new vector denoted by A times B, and those vector has these entries. The weird entry. It seems like there's no rule, but there is actually a rule. So let me restate this formula in matrix determinant way. So A times B is given by the first determinant of 3 by 3 matrix, where first row is given by the vector I, j, k, where we call that I is given by 1, 0, 0, and j is given by 0, 1, 0, and k is given by 0, 0, 1. And then the second and third row are the entries of vector A and vector B. So here are A and B. So since I'm talking about the determinant of this matrix, let's compute this using the definition. So first I'm taking all the plus sign entries, I times A2 times B3, and then second, J times A3 times B1. I'm doing this, I'm doing this one and this one and this one here. And then K times A1 B2. And then let's take the negative parts. So negative parts comes here, here, and here. So I get minus of K times B1 times A2 minus I times B2 times A3 minus J times A1 times B3. So other than I, j, k, they are all scalars. So it's basically a vector multiplication with the scalar. So take the I vector together, we get A2 B3 minus A3 B2 I and A3 B1 minus A1 B3 J, and then A1 plus B2 minus B1 A2 K. So that's how we define the A times A cross product with B. So what's the meaning of this cross product? Yeah, so first of all, let me rewrite the remark as a remark. So if A, the vector A and vector B, A and B are not parallel, then A times B is a normal direction. So this normal means perpendicular direction to the plane containing these two vectors A, B. So suppose you have A vector and B vector coming from the origin, and there should be some plane containing both A and B. So this A times B is the normal direction, the perpendicular direction to this plane P. A times B. So I'm only talking about the direction of this cross product. I'm not saying that this cross product is always normal vectors. I'm just saying the direction is normal. Okay. All right. So there are other properties on this cross product. Let's look at one by one. So A cross product 0, I'm just calling it as A times B, is equal to 0, because whenever I have 0 in one row, then everything goes to 0. So same thing for 0 times A. And if I take the cross product of A times A together, then I get 0 vector. This can be explained by using the theorem that we're going to cover in the next slide, but you can also explain the second property using the properties of determinant of matrix. So look at the 3 by 3 matrix to define the cross product of two vectors. You have the entries of A in the second row and the B entries of B in the third row. So when I take the cross product of A and A itself A, then I get second row and third row the same thing here, right? So there's the properties in the determinant that if two rows of the matrix is the same, then the determinant is 0. So you have second and third row equal as the entries of vector A, so therefore you get the 0 always. So that's how you can prove this second properties using only the properties of determinant. And now this one says if you take the cross product A to B, or then it's negative direction to B to A. If A and B are the same, that's 0 vector, so it doesn't matter. 0 is equal to negative 0. You can also consider this as a right-hand rule, that if you take A to B direction, let's say you have, let's say, so here is a thumb, and here's a right hand. Okay, and this is the thumb. So you're sweeping A to B in this direction, and the cross product points to the same direction of where your thumb pointing. Okay, so that's the right hand rule. So if you have a cross product B to A, then you get opposite, right? So you get, so this is the opposite right hand. You get the inverse direction here. So this direction is B times A. Okay, both are right hand. Okay, and the rest of the properties are kind of obvious. Well, maybe not obvious for the second one. A seventh property is not that obvious, but it's not hard to show. So first of all, if you have a scalar multiple K, then you can move around your K, as similar to the matrix case, and also you can distribute your cross product to the sum of two vectors, and then you can combine your cross product with another vector dot product. So think about this one. So this is interesting, yes. So when you do this, first let's look at the first one here. A dot product with A cross B, then it's always 0. So why is it 0? So think about A cross product B. What you get is some constant coefficient I plus some coefficient J, some coefficient K, and you can represent this by, let's say, let's give a name here. So A, B, C, and let's say this is A cross product B. So I can rewrite this as A, B, C. So I know that how to write this capital A, B, C in specifically in terms of the coordinates of A, B, but I'm just using a simple notation. And let's say I'm going to take an inner product with A of A cross product B. So what I'm doing is that I take A1, A2, A3, and then cross product with large A, large B, and large C, right? So result is A times A1 plus B times A2 plus C times A3. But these results, let's see, this one is exactly the same when I replace this IJK with A1, A2, A3, right? So in this formula of A times B here, if I simply replace IJK by the entries of vector A, A1, A2, A3, I get the result of A dot product with A times B, right? So I can rewrite this A dot product of A times B simply as just replace IJK with the entry of vector A, A1, A2, A3, and everything rest of the parts is the same as definition of cross product, B2, B3, right? So if it's confusing, then just forget about what we are doing here. Think about the cross product definition of cross product again. So in the first row we used IJK, right? But when we actually try to compute this dot product with A, I'm simply getting the same answer, same result by replacing IJK with the entry A1, A2, A3. So what I'm doing here is that replacing IJK with A1, A2, A3. So what we get is A1, A2, A3 on the first and the second row. So as I mentioned earlier, if you have the same two row or actually column, then the determinant of the matrix is always 0. So that's why we get 0 here, right here in this sixth property. And same thing for when you take an inner product with B. Okay. And you can also reinterpret this as a geometrically that A times B is perpendicular to the plane containing A and B. So therefore A times B must be perpendicular to A and B, right? So whenever two vectors are perpendicular, you get the 0 when you take the dot product. So that's how you can also explain this property C. So this is also important. And 7, this is just a simple property. It's not really important. I don't ever use these properties in application, but simply it says that it works. Okay, so if you can even take the cross product and cross product, so you have a 3x3 matrix here, and also so 3-dimensional vectors here, and C is also 3-dimensional vectors, so you can take the cross product again with 2 vectors, and what you get is another vector. This is also 3-dimensional vector, but with a different direction than A and B. It simply has a coefficient on B with this inner product and coefficient of A as this product, and you can simply compute left and right hand side by assigning a random variable in A and B and C to find out that this equality always true. Alright, so this theorem is similar to the theorem that we discussed in the earlier about the dot product. It's a little bit different. One thing that it shows that is that the norm of the cross product is equals to these value. So norm is always positive or 0. So this part left hand or right hand side is always positive or zero number. And it says the theta is the angle between A and B, and you get the sine theta, right? So you can also prove this, let's say, you can also prove this using the cosine and sine rule, but let me give the specific version of the proof of this theorem. So even though this A, B are three-dimensional vectors, I want to put that in the two-dimensional plane, and I want to look at this two-dimensional plane as my XY plane. So here's the thing. So here you have A and B, and this is the origin in three-dimensional space, and this plane may not be the XY plane, but I want to look at as if it's a XY plane by rearranging my axis, XY and Z axis. So consider P as XY plane here. So somewhere here we have X axis, and here we have Y axis. So then I can rewrite my A, and let's say here we have Z axis as so my size of vector A times cosine theta 1, sine theta 1, and 0, and B is size of B times cosine theta 2, sine theta 2, and 0. So since AB are contained in XY plane, there's no Z direction, and theta 1, theta 2 are the angle between the vector A and B with the positive direction of X axis. And then let's take the X, A and B cross product. So we have a scalar multiple norm A, norm B, so we have A, B coming out from the properties of the vectors, cross product of vectors, and then use the definition of cross product IJK, cosine theta 1, sine theta 1 and 0, and cosine theta 2, sine theta 2, 0. So whenever you compute the coefficient of I and j, there are 0, which makes every coefficient becomes 0. So what we left is only the k part, right? So k has coefficient c1 s theta 2 minus c theta 2 sine theta 1, right? So these are coefficient of k. Okay. So I want to take the norm of this cross product, not the cross product itself. Okay, I know that direction is always k direction, the z direction. Right? So norm is, don't forget this norm, A and B, and the size of cosine theta 1, sine theta 2 minus cosine theta 2, or just rearrange this, sine theta 1, cosine theta 2. By the sine rule or cosine rule, you get the sine theta 1 minus theta 2, right? So this is equals to A, B, wish I have a more space here, theta 1 minus theta 2. Okay, right? So since we took the absolute value sign here, it doesn't matter whether I took the theta 1 minus theta 2 or theta 2 minus theta 1, although the sign of sine changes, but because I take the absolute value, it doesn't matter. So that's how I get this. And there's a geometric meaning of this cross product from this theorem. So whenever you have A, B, two vectors, and you consider this as a three-dimensional vector lying on two-dimensional plane, then you can take the parallelogram whose two sides are A and B, and the area of this parallelogram is A cross product B, norm of this vector. Because of this right hand side, you have the length of A and length of B times sine theta, so you get the height of this parallelogram, right? So it makes sense when you reconsider these properties too, right? Whenever you take the one vector and cross product to itself, then you get a parallelogram who's flat out so that there's no area at all. So it makes sense that you get the zero vector when you take the cross product of itself. And also, if you take the first properties, that if you have no length on one side of parallelogram, you always get a zero area. So if you have any question, please ask anytime. Okay, so we'll keep moving here. Okay, so that's actually we already discussed some of these parts, and this is the proposition on properties of determinant. Let me just read through these propositions. So let's say I'm going to write the determinant of A by the bar A, then the following holds. So if you have a row whose entire entries are if one row is all zero, then you always get a zero determinant. And if you get another matrix by switching two rows, then you get an inverse sign, the reversed sign of determinant. Okay. And if you take another matrix by multiplying one row of a given matrix A and add it to another row, then you get the same determinant. So here's the thing. I think the first one and second one is kind of obvious what they're talking about. The third part is talking about this situation. So you have A11, A12, and so on, and A1, 31, and 31, A32, and A33, A13. Okay, so this is our A, and I want to make B by taking the first row here and then multiply C and then add it to the third row. So what I get by as a B is that first row is the same and second row is also the same, but third row it now become A31 plus CA11 and okay, let's rewrite here. A32 plus C A12 and A13 and then A33 plus C13. Okay, so these two matrices are different. Obviously you have a different third row as long as C is not 0, but the determinant of A and B are the same. Okay, so determinant doesn't change when you do this kind of operation. Right, I don't think that will ever appear in this course. Probably this is more suitable in the linear algebra course. So we are talking about the inverse of matrix. So whenever you want to take a notation of inverse of matrix, you need a square matrix. Square matrix is the matrix where the number of row and number of columns are the same. Square matrix. Now if you have a matrix B satisfying this equality, that A times B and B times A is equals to identity matrix, where identity matrix of size n is one that has 1 and on the diagonal and 0 elsewhere. Okay, then it's called the inverse of A. Okay, inverse of matrix A, and we denote that matrix B as A to the negative 1, just like the reciprocal of number. And if there's an inverse matrix, then we call matrix A as non-singular matrix, and if there's no inverse matrix, then it's called singular. Why we call it singular and non-singular, it becomes obvious when you take the linear algebra course and you relate it to as the existence of solutions of the system of equations and so on. And there is an easy way to check whether a matrix is a square matrix is singular or not. If the determinant is 0, it's always singular, and if it's singular, then its determinant is 0. So determinant is important when you check whether the matrix is singular or not. And why singular is important will appear in the linear algebra. We're not going to go deeper into that. By the way, there is some meaning of the singularity of the matrix when we're talking about the transformation later, but we will talk about that when it comes up. So for now, just think about why this happens. Just think about there is a definition like this, and let's suppose that we have a non-singular matrix. Okay, since we have a non-singular matrix, determinant must not be 0, so we can take the determinant as a numerator of this fraction. Then our inverse matrix can be written as this matrix. So you have switched diagonal entries, switch diagonal entries, and then you take the negative sign. Let's see, A2, A12. I'm sorry, there's a typo. You shouldn't change this. So here is 2-1. This is 1-2. It's a serious typo. And then, so this is the first step to get the inverse, and second step is take the negative sign to the off diagonal entry. Okay, so that's the inverse matrix of 2x2 matrix. And how do you get the inverse matrix of 3x3 matrix? It's a little bit complicated. So you do this. So first of all, you take the 1 over determinant of B, and the rest of the entries are given as follows. So first of all, I want to get the first row, first column entries of inverse matrix of the 3x3 matrix B. Then this one is obtained by removing the first row and first column of the matrix B and take the determinant of the remaining 2x2 matrix. Let me explain that in the picture here. So here's B11, B12, B1, or maybe I just use this. Okay, do I use this for another example? So I want to find, suppose that I want to find C11. Okay, then I erase first row, first column, because C11 has the first row, first one, and index here. And then remaining 2x2 matrix consists of B22, B3, B23, B32, and B33. So I take the determinant of this matrix is C11. Okay. So when you have C21, you did it similar. So here, when you have, if you want to find the C21, then you erase the second row, first column, because of the C21, okay? And then the remaining 2 by 2 matrix consists of these blue parts. You take the determinant, and that becomes your C21, okay? Now, important thing about this C1, C2, Cij is that when you take an inverse matrix of B, Cij is not the ith row jth entry of the inverse matrix B. Cij is the jth row ith column entry. So you switch the role of the first index and second index. So you see C12 appears on the second row, first column. Okay. So C12 is obtained by erasing first row, second column, but it is placed on the second row, first column entry of the inverse matrix of B. So you switch the role of first index and second index. And then more importantly, you have to put the signs on in this in these tiles. So you have minus signs on these areas, not everywhere. Okay, like a checkerboard, you have a negative sign on the checker signs here. So that's a B inverse. You can generalize this kind of formulation to n by n inverse of n by n matrices, but we're not going to ever use that. I don't think we'll ever use this formula, because once you know how to compute the inverse matrix by MATLAB, then you don't need to do this by yourself, by hand. But it's good to know, but you have to know the definition at least. So let's summarize, let's finish off by stating the general definition of vector space. So far we talked about the vectors and matrices and some properties of matrices, and let's go back to the original definition of vectors. So I used the vector as n tuple of real numbers, but in fact anything can be vectors. Okay, so you have to define the vector space first, and then what is the vector inside that space. So the vector space is the set of elements, and that element is sometimes called the vectors, satisfying 3 properties. First one is that it has a zero vector, satisfying this algebraic property, and there should be a vector sum, which means that you have an plus operation, adding an additive operation between 2 vectors, which is the elements of the vector space V. And you need a scalar multiplication. If you take any real number, you can multiply your scalar to any vector and you get another element in the vector space. If any set satisfies these 3 properties, then it's called the vector space, and the elements are called vectors. So not only the n tuples of real numbers, but there are other elements that can be defined as a vector. So for example, obvious example should be a matrix, but a less obvious example is the set of functions. So let's say we have set of all differentiable function defined on the real number. So a single variable function. Differentiable means that you can take a differential of the function at any point, and the derivative is also continuous. Derivatives are also continuous. And suppose that you have 2 such functions in this set. You can define an add f plus g as a new function, which gives the value added, which if you take any x in the real number, then f times f plus g is a new function whose value at x is simply fx plus gx. Okay, so let me rewrite this. CR is a function from real number to real number where f is continuously differentiable. Let me rewrite it. Continuously differentiable. Okay. Now, if you define your f plus g as this function, it's obvious that f plus g is also a differentiable function because f plus g derivative is same as the sum of two function f prime and g prime, right? And therefore vector sum is well defined, and if you have a scalar k, then kf is also continuously differentiable because simply it's a differentiable function and you just multiply your k. And there is a zero function, so if you have f equals to 0, that it gives 0 for any value of x. It's also continuously differentiable. It's a constant function. So it satisfies three properties of vector space. So this C1R is a vector space. Okay. You can generalize these concepts to CNR, where you can take the derivative n times, and then you still get the continuous function that is called the Cn function, and so on. So unlike our n-tuple of numbers, set of n-tuples of numbers, this kind of vector space is infinite dimensional. You don't have a dimension. It's a dimensionless. It's infinite. So another definition of a vector space is that you can take a space of a line. Okay, so let's say Vk to be defined as this set. So you collect all the pairs of points in two-dimensional plane where the second coordinate y is a multiple of the first coordinate by factor k. So k is fixed. So if k is 0, then you always get an x-axis, and if k is not 0, you get a tilted line. So whenever you have this line with slope equals to k, all the points lying on this line is called Vk. Now, Vk is a vector space. Why? It contains 0, right? 0, 0. It serves as a 0 vector in Vk. And you can add two vectors, x0, y0, and x1, y1. If these two vectors lie in Vk, then you can add these two numbers, x1, x0, x1, and y0, y1 is also in Vk, because if we take k times x0 plus x1, then it's k times x0, k times x1, and that's equals to y0, y1, by the assumption that these x0, y0, x1, y1 lies in the Vk. Okay. What's another rule? Scalar multiplication. So let's say we have L as a real number and x0, y0 lies in Vk, then L times x0, y0, which is Lx0, Ly0, also lies in Vk, because if you take k times of Lx0, this is the L times kx0, and kx0 is y0, this is Ly0. So this fits to the definition of Vk. Okay, So if k ranges from negative infinity to positive infinity, then it sweeps the entire line passing through the origin inside of the two-dimensional plane, but except one line, which is the vertical line, the y-axis. So you can redefine your y-axis line by v infinity. Suppose that, from the fact that your slope is infinite. And these vk and v infinite are all vector spaces, but also it's called a vector subspace of the entire real line R2. Okay. So R2 is also a vector space if you consider three properties of vector space, and vk and v infinity are subspace of a subset of this vector space R2, and also it's a vector space, so therefore it's called a vector subspace. Okay. Okay, so let's keep moving here. So example. So let's P be the set of all points on the plane, two-dimensional plane in three-dimensional space. And by identifying the points in P as position vectors, we can say P is a vector subspace of R3. So here is a plane P. Okay. And here is the origin. So P contains the origin because of this equation, defining equation. I want to take the point inside of this plane P as a vector, assuming that if I have a point A, then my vector is OA position vector. Okay. Then P becomes the two-dimensional vector subspace of three-dimensional vector space R3. Okay. Now suppose that you have two vector subspaces, V and W. You can take the intersection of these two sets, okay, and that becomes still a vector subspace of n-dimensional vector space Rn. Okay. For example, let's say I have another plane. Let me draw it like this one. Let's say I have another plane called H. Okay. Then intersection, if P and H are transversal, which means that it's not parallel, then the intersection becomes this line, right? So this is P intersection H. This is the line passing through 0. And this becomes still one-dimensional vector subspace of three-dimensional space. So this is one-dimensional vector subspace of R3. Okay. So whenever you have a two vector subspace in a big vector space, then you can take an intersection between two vector subspaces and you get still another vector subspace. And so when you're talking about the vector space, the natural concept is the basis. So we already talked about the basis, the natural canonical basis of Rn, E1 to En. But in general, there could be another basis, and if n vectors v1 to vm satisfies this property on the vector subspace W, then it's called the vector which spans the vector subspace. So suppose that we have W defined by this linear sum of elements v1 to vm. With a coefficient in any real number, then we call this W as a vector subspace spanned by these vectors. Okay, and we denote by this way. So in other words, let's say, for example, R3 is spanned by IJK. Okay, And then let's say v0 lying inside of R3. That was the previous example when k is 0. So that's the x-axis in R3. Then v0 is spanned by just one vector, because v0 it consists of x0, 0. Let's say in the previous example we didn't mention this in R3, so let's say in R2. Okay, so let's rewrite this in here, E1. Okay, so V0 is consists of x lying in R. Okay, and this x0 can be written as x times 1, 0, which is x times E1, right? So we can rewrite this. And in general, when you have n-dimensional vector space, then this is always spanned by E1 to En, okay, and so on. Now, once you know the concept of span, then you have to consider what's the minimal set which spans the given vector space. So suppose that you have v1 to vn, which spans the vector v. Then any vector by definition can be written as a linear sum of these vectors. If this set satisfies this property, then it's called a linear independent. The property says that if there is a coefficient that linear combination with v1 to vn with that coefficient makes the zero vector, then this a1 and an are all 0. So only way you can make a zero vector by linear combination of v1 vn is taking a coefficient 0 everywhere. Then this set of vectors is called a linear independent vectors. So here's an example. E1, E2 are linearly independent. Why? Because if you want to make a zero vector out of linear combination of E1 and E2 using coefficient A1 and A2, then A1, A2 vector must be zero vector, which means that A1 and A2 must be all 0. Right? So E1, E2 are linearly independent, and it spans the two-dimensional plane R2. R2 is spanned by E1 and E2. Okay. So when you have a set of vectors which is linearly independent and it spans a vector space, then this set is called a basis. And element of the basis is called a basis vector. So for example, E1, E2 are basis vectors of R2. That's why we discussed this EI as a basis vector in the earlier slides. Okay, so far this is the content what we want to talk about, and from now on we are going to talk about some problems. Has any questions? Okay, so as I mentioned, the problem is your homework, but I will solve the problem with you. But you have to rewrite your solution by your own language using the typing method and submit as a PDF file. If you don't have time, I will skip the solution sometimes, but we have only few problems here, so I probably do all of the problems. Okay, so let's look at the first problem in the first slide. Show that the vectors, two vectors, this is this is one, and this is second, are orthogonal. If you want to show any two vectors are orthogonal, you need to take the dot product, right? So first one, let's take dot product of BA, AB, and BA minus AB. So you can use the distribution rule. I will answer that question right after I solve this. I write the solution here. So B norm square A inner product A, and then A B and B inner product A minus B A B inner product and minus A square B inner product B. So when you take the inner product itself, you get the norm square B square and A square and A. So here you get canceling out, right? You get this guy is cancelled out with this guy. So and then minus A square B square, and they're 0. Okay. Alright, so question is, if you have a set which spans a vector space, does that set should always be a linear independent? No. You can have a linearly dependent set of vectors which spans a vector space. If you have a linearly independent set of vectors which spans a vector space, that becomes the basis. Okay. But if you have a linearly dependent set of vectors which spans a vector space, it's not a basis. Okay. Alright, so let's look at the second problem here. Show that this bisects the angle between A and B. So suppose that we have A and B. It says that BA plus AB bisects these angles by theta. So all we have to do is find the inner product and showing that these angles are the same. So cosine theta can be, so let's say theta 1 and theta 2 here. Cosine theta 1 is obtained by dividing the size of A, and size of B, A, B, size of these vector, and then B, A plus A, B, inner product with A, right? And how let's keep compute here. So denominator and B and A square and A and A dot B. How about cosine theta 2? So B times big thing, so I'm not going to rewrite this everything. So we have B A B times B. So we get B A times B, and then A times B square, right? So I want to show that these are equal. These two things are equal. So let's cancel out B here, B, and B here. And here we cancel out A, and A here. So denominator are same as these guy, right? The norm of these big vector. And numerator becomes A dot B plus A norm times B norm. A norm times B norm. So numerator and denominator are the same. So we have the theta cosine values are the same, and therefore we have theta 1, theta 2 are the same. Okay. So problem. Now you want to find the equation of a plane. I want to find the distance between the plane and the line. So line passes through this point and parallel to this vector. And so it's a plane, not a plane, so it's just a point. Okay, so I want to find the distance between the point and the line. Now let's say this is our line and here is our point. If point lies in the line, we are assuming that this is distance is 0, but it's not on the line. I want to take the projection of the plane of the point to the line perpendicular way and find the distance of this between 2 points P and H. Okay, so how do we do that? So first of all, let's pick a random point here. Okay, let's pick 2, 3, minus 2, which is given when t equals to 0. And I want to take a position vector. Let's say this is Q, QP. Okay, and then there is a direction V parallel to L. Let's say this is V. So V is minus 1, 1, 2. Okay, so I'm going to take a projection of position vector QP onto the direction of V. So that's what I do. So projection of QP onto the direction of V. So when you compute this, you get some three-dimensional vectors. What you have to do is, let's say this is our, suppose that this is our so when you do this, you get this QH vector, right? What we want to find is the length of PH vector, norm of PH vector, right? But PH vector is given by QP vector minus QH vector. Okay, so we know what QP vector is. That's obvious by given in the problem. Okay, and by taking the projection, we get QH vector. Just subtract that and then take the norm of this result. You get the PH. How about the second one? So find the distance between two parallel planes. So why do we know that? How do we know that these are parallel? So you see the coefficient out on XYZ here, 2, minus 2, and 1. So these are the normal direction of the planes, and these normal directions are the same. But here we have different coefficient here, 5 and 20. So they are not the same plane, but parallel. So how do you find the distance of two parallel plane? You first pick a point, and then you pick a random line here, and then you find the distance between these point and the line. Or I'm sorry, so this is not the way we can do this. So first of all, you pick a random point on one plane. So let's say this is plane P and this is plane H. Okay, so this is P and this is H. Let's say we have 0, 0, 5 in plane P. Okay, and let's pick another random point on the plane H. Let's say I want to pick 0, 0, 20. Okay, 0, 0, 20, right? So let's take a vector from these 2 points. Let's say this is point A and this is point B. I want to project my AB vector onto the normal vector of these 2 planes, where V is 2, minus 2, 1. So I draw it a little bit weird way, so let me draw this again. So let's say 0, 0, 20 is here, and this direction is my normal direction. Okay, so I want to project my vector AB onto this normal direction. So I get this vector. This is projection of AB onto V. And then you take the norm of this vector. That's the length between 2 perpendicular planes, 2 parallel planes. Okay, does that make sense? Since you already compute the projection specifically in previous problems, I'm not going to do this again, but I'm just giving you how to solve these questions. If you have any questions or don't understand anything, please stop me anytime. And third one, find the distance between 2 skew line. Okay, so we have a line here and we have also another line here. So I want to find out the minimal distance between 2 points. So if I pick a point from 2 lines far away each other, it could be an infinite, but I want to find 2 points which are close each other, the most closest each other. So in other words, I want to find the line that passes through each line perpendicular way. Okay, so one way you can do this is by sending one line to the upper line. So let's say this is L1 and this is L2, and this dot line is a parallel translation of line L2. Let's say this is L2 prime. Okay, and then there must be a plane containing both L1 and L2, right? So the question is, what's the distance between P and L2? That's the distance between L1 and L2. Okay, so how do you get the distance between P and L2? So you do the similar way. So you pick a random point here. So if it's very lucky, then you might get a point. Well, it doesn't matter. So just pick a point here. So let's say we have A. Let's say minus 1, 2, 0 when t equals 0. Okay, and then let's see. And then let's pick another one point here. So let's pick a point inside of the plane P. So let's see. I can pick a point in L1. So let's say this is point 0, 5, minus 1, which is B. Okay, so there is a vector A to B. Well, it seems like it's already perpendicular, so let's take another one here. So let's say, well, let's say this is B. Okay. 0, 5, minus 1, and take this vector A to B. Okay. And what we do is projection again. So I want to project my vector AB to the normal direction of the plane P. So let's say V is the normal vector to P. So how do we get the normal vector to B? This is done by cross product two direction vectors of the line. 2, 1, 3 cross 1 minus 0. So L1 has direction, let's say this is direction 2, 1, 3, and L2 has direction 1 minus 0. So these two vectors are both parallel to the plane P, right? If you take the cross product, you get the direction which is perpendicular to both 2, 1, 3 and 1 minus 1, 0. So that's the normal direction of P. So that's how you get the V, and then the projection of AB onto this vector is the vector which is perpendicular to the line L2 and also line P, which connects the two, which start from the L2 and ends up at plane P. So therefore, if you take the norm of that vector, that's the distance. L1 and L2. Okay, make sense? Okay, so this problem is about the matrix again. So I want to show that if there is a 3 vectors A, B, C, then this quantity is equals to the determinant of this 3 by 3 matrix. I need to use the properties of matrices, determinants of matrices. First of all, think about C times C dot A cross B. So we mentioned that this is equals to replacing I, J, K places by entries of C. C1, C2, C3, and A1, A2, A3, and B1, B2, B3. Now, when you switch the row and two rows, the sign changes. The sign of determinants change. That's the property 2. Property 2 of the determinant. Let me go back to this number of slide number here. So where was it? Here, proposition 2 here. Yeah. So 23. Okay. So I want to switch these two rows. Okay, so we have A1, A2, A3, and C1, C2, C3. And then use the same property again on the second and third row. You get A1, A2, A3, and B1, B2, B3, and C2, C3. that's how you get the inequality. Alright, so I think that's the last one. Okay, so I didn't put this the picture here. The picture is in the textbook actually. So imagine two concentric circle. So let me draw the two concentric circle here. Concentric means that it shares the common center with radius a and b. So b is larger one, b is smaller one, b and a, which rolls on the flat line. So rolls on the flat line, which with the same angular velocity. So it rolls with the same two circles are stick together and then rolls. Okay. A curvative cycloid is the trajectory of a point on the circle of radius b. So you have an inner circle here, and let's say I start from this point. Okay, so this is our point P, and when this larger circle rolls, there's a trajectory of P this way. Okay, so let's say if the larger circle is right here, then point P is moved up here. Okay, so this is B and this is A. Let's say P prime. Okay. So find the set of parametric equation for the curvative cycloid with A equals to 3 and B equals to 2. I will set up the equation, and then in the MATLAB session we'll show you how to draw this picture. So let's say this is our 0,0 point. So in the initial position, let's say P was at 0, B, so right above the ground here. I'm sorry, it's not B. I'm sorry, so A minus B, right? So I want to find out how far this center went at the time t. So let's say the angular velocity t is t radian per second. Okay, so it rolls 1 radian in 1 second. So after it rolls 1 second or t second, it moves to the direction, so this direction. So this is when time passes by t second. So this is at, right? So your center is at where? So let's say O prime here. So this is O. So O prime is at at, comma A, because that's the center of the radius A circle. And so that's the vector from origin O, as this the origin. Sorry, so this should be A here. So that's the vector from A to O prime. Okay. I want to find the position vector from A to P prime. So A to P prime is actually equals to A to O prime plus O prime to P prime. How do you get O prime P prime vector? So let's find out what happens to the inside circle. So inside, it rotates to the clockwise by set t degree, right? So when you rotate your angle from 0, so you start from cosine 1 over 2. Sorry, so it's minus 1 over 2, pi over 2. So P OP is originally was it's on in the bottom here. So OP vector is B times b times of cosine minus pi over 2 sine minus pi over 2, right? So when it rotates, O prime P prime becomes b times cosine minus pi over 2 plus, I'm sorry, so it's a negative, so minus 1 over 2 pi over 2 plus theta, I'm sorry, t, comma sine minus pi over 2 plus t, right? Because it moves clockwise, and when you move clockwise, that your angle start from this direction, right, which is minus pi over 2 degree, and then keep moving in this direction by theta or by t, right, at time t. So you keep moving and keep minimize, keep subtracting your t here. Since cosine is an even function, I can get rid of this, and sine is an odd function, I can get rid of this minus to the outside of sine. So these are the AP prime. So let's say this is rewrite AO, which is AT comma A plus B. Can I rewrite this? So cosine is so we have minus sine t and then here we have minus cosine t. Okay, so that's our AP prime. So parametric equation, that's the xt times yt, right? So xt is at minus b sine t, and yt is a minus b cosine t. These are the set of functions.